Welcome to Unit 1, our Introduction to Chemistry. This is likely the first video lecture you've seen of mine. They generally will involve me going through the slides talking about them, but feel free to at any time pause, go back a slide, try and figure out what in the world I said. But if you have any questions, also feel free to ask me the next day in class. So yeah, these are our objectives for Unit 1. They're also found on the first page of your notes. And that gives you a summary of really what we're doing in Unit 1. My goal is that at the end of the unit, you can do all these objectives. In fact, your test for Unit 1 was built by me choosing questions that basically assess these objectives. So if you can distinguish between the three states of matter, then if you can do all these objectives, you'll ace my test. In addition, if you get some questions wrong in your test, we'll actually be able to bring them back to a certain objective and really show, oh, this is what you got stuck on. You'll even see these are sorted in your notes. So not only can you figure out what you did wrong, I can also point you to where in the notes it shows you how to do it correctly. So yeah. So our first objective in our first little section that we're going to talk about is to explain how a periodic table is useful. You will notice that we are starting with objective 2.3.4. These numbers are actually numbers from a book that I'm using. They really don't matter too much for you. They're more for my organization, so don't worry about the numbers, except for helping you determine what problems you got wrong or where you want to study, etc. So, chemistry can be summarized in two words, matter and energy. Matter is defined as anything that has mass and volume. Sometimes you've heard this as takes up space. Well, space is basically volume, and so if something has volume, then it's taking up space. So, same thing, less words. Whereas energy is defined as the capacity to do work. We will sort of talk about what work is, but not really. That's more in AP Chem or more specifically in physics. But chemistry, matter and energy. All matter is composed of atoms, which are made up of three main ingredients, if you will: protons, neutrons, and electrons. These three particles, which is actually our normal word for them, are called the subatomic particles. Notice that sub normally means below or lower than, if you will, and atomic really just means atom. So these are kind of the particles that are smaller than atoms, which makes sense since atoms are made up of these particles. All chemical identity, meaning our name, anything that we associate with it, is determined by the protons. But all chemical reactions occur due to the electrons. Hopefully you're asking what happens with the neutrons. We'll talk about those a little bit later. A group of atoms that all have the same chemical identity is called an element. To date, we know of 118 elements. We store that information, at least what information we can, on that of these elements on our periodic table, which is that thing you've probably seen somewhere that looks something a lot like this. So each individual square of that often has a few things about it. I actually don't remember any of the other numbers that go there, which is kind of weird. But you'll see numbers here and here, sometimes a little bit of stuff here. All that is information about the element indicated by that symbol and determined, normally by this number, by their amount of protons. So, this is an actual example of a periodic table. You'll notice there's stuff missing here. It's a little bit old. At this time, we actually did not know the names of them. We knew that elements existed, but we had no name for them, so this is left out. Anyways, our periodic table, as you can actually tell by the chart, is normally organized into four main blocks. I will tell you, this actually should be purple. For now, just trust me on that. We'll explain that a lot more later. But you've got our first two columns are the S block. We'll definitely talk about that more later, but just showing you what they're called. Our second block is actually our P block, which is the right 6 columns. The middle 10 is our D block. Our F block actually fits in right about here, but that's normally this kind of extra 14 columns. I will tell you they're separate only because they simply do not fit very easily on the periodic table. So we tend to take them out and kind of put them by themselves. But that's the general periodic table. The SPDF definitely is informative. We'll talk about that in Unit 3. For now, though, you do need to know where the S block starts, or the P, or the D, etc. So, specifically notes-wise, 4 blocks, SPDF, talk about them later. And on that periodic table, we had a jagged line. So if I were to draw this section, I'm going to ignore the F block for now. Normally you'll see a jagged line right about here. On the periodic table in our classroom, it's blue. It's actually just kind of painter's tape that we put there. So any element to the left of this, actually I will draw the F block because they're actually included. So any of these, and the F block, since it actually comes right from there, are called metals. Anything to the right of this is called a nonmetal. Anything right along it that's actually touching it is a metalloid. I will tell you that metalloids are mainly those that I just covered, but for ease of learning, you can treat them all as metalloids. Makes your life a lot easier. So, metals, nonmetals, metalloids. In addition, on the periodic table, we have columns that go up and down, and rows that go side to side. Columns on the periodic table are also called families or groups. Normally the group refers to the column, and we use the term family if it actually has like a special name to it. Rows, however, are always called periods, which does deal with the name periodic table. We'll get to that in unit, I believe, 3. Most groups, though, are referred to by number. Again, most columns are referred to by number. 8 in particular are named. There are a few more, we don't care, but those are the main 8 families that we will talk about. Again, a group that is not named is just a group. If a group or column has a name, it's a family. It's a little confusing. So, to give you an illustration, these, purple one, does not have any specific name with the column. You can tell that by the colors above. Yes, it's part of transition metals, but this column isn't very special. That means we'd really only call this group 6. We wouldn't call it family 6. However, this column, make sure you notice that hydrogen is not part of it, does have a name. It's the alkali metals. So yes, we can call this group 1, but we can also call it the alkali metal family. Normally, though, I will say we tend to just use the word group 1. Kind of makes our life easier. These are the alkaline earth metals, sorry. Sometimes you'll see just alkaline. Normally it's alkaline earth. We have the noble gases. We have the halogens. You can also see the nonmetals. The halogens are nonmetals too. They just have a special name that we normally think of before we just call them the halogens. These gray are kind of other metals. They are metals, they're just not transition ones. And yeah. So, specifically, we also have a few elements that, not being in an actual column, they're still similar enough that we give them a name. So the lanthanide series are elements 57 through 70, which on our F block is the top part. The actinide series are the bottom part. By the way, this element right here on your periodic table is lanthanum, and this is actinide. Sorry, lanthanide, actinide. Anyways, transactinide elements are elements basically after these series of elements 103 to 118. transuranium are the elements after uranium. Of these, you mainly need to know these. Transactinide and transuranium are great. You may see them, but I'm not going to ask you many questions about them. But we have seen them enough, that's why I'm telling you. So mainly notice that we've got lanthanide and actinide series. By the way, that squeaking is my chair, in case you haven't figured that out. So while the transuranium can be found in two different groups, important thing to know is they are radioactive and unstable. A lot of the radioactive elements you can think of are transuranium. That's about the only thing you need to know of them. Don't really worry about locating them. We've been able to synthesize temporary versions, but really can't find them in nature. So if we get to it, we'll talk about that in our nuclear chemistry unit, which will be our very last unit of the year. So, yeah. All right, so for the following elements, let's indicate what type of element they are. Type of element goes back to metal, non-metal, metalloid. What group, period, and finally, what named family they belong to, if any. All right, sodium, for example, is in our first group. It's in our first column. It is in our third period, as it's in our third row. And finally, it's an alkali metal. I'm just going to put alkali because there's only one alkali type thing. Carbon is in our 14th period, or 14th group. Second period, and it doesn't have any actual group or family it belongs to. Helium is in our 18th column, our first period, and is a noble gas. Aluminum is in our 13th group, in our third period, and is not part of any named family. By the way, I'm looking at a periodic table while I'm doing all this. So I'm not doing this from memory. I tried, it didn't work. Make sure you're actually looking at one when you do these. Iron is, hang on, my periodic table fell asleep. And by that I mean, well, my phone. This is in our 8th group. It is in the 4th period. It's our 4th row down. And it does not have any named family with it. So there you go. That's how we use our periodic table. Now, in our next section, we have a different objective. We have that students can identify 3 broad classes of elements and distinguish between them. Metals, as we mentioned earlier, are to the right of the jagged line, are commonly identified by their luster, which is like the chemical word for shininess. Generally, metals are shiny. They're also very good conductors of heat and electricity, meaning you can send an electric current through them, or they also heat up very quickly. If you've ever had a metal coffee cup, it's really not that useful. It will hold your coffee very well, but your hand's going to be very hot. Finally, they're also malleable, which means smushable. You can kind of smush them into a different shape, kind of think of Play-Doh. And they're ductile, which means I can pull them into a thin rope or wire without it actually breaking. For example, copper, we have copper wire almost everywhere. But if you think of something like chalk or something, or a piece of wood, you can't really pull it into a thin rope. Ductile is a bit weird, but hopefully that helped explain it a bit. Nonmetals are about the exact opposite. They are not very shiny, they lack luster, and they do not conduct heat or electricity. These are things like rubber, which do not conduct electricity, or things like some plastics, some ceramic, just thinking of other different coffee cups, if you will, that may heat up, just not very fast, especially when compared to metals. Metalloids, which are on the jagged line, have traits of both. Some are shiny, some aren't. Some conduct heat, some conduct electricity, some don't. They're not as easily sorted, except for the fact that there's some combination of a metal and a non-metal. This brings us into our next section. Our objective for this is that students can distinguish between the three states of matter, which is kind of why this section is called States of Matter. So as a reminder, matter is anything that has mass and volume. Now, mass is defined as the amount of matter a substance contains, and volume is defined as the amount of space a substance takes up. Now, please don't ask me what matter is, because that kind of goes into a property of mass. We'll talk about that a little bit later. You really don't need to know. But you just need to know that mass is how much stuff something has, basically, normally measured in grams. We'll mention that later. And volume is how much space. So, as another reminder, all matter is made up of atoms. It's one of the first things we talked about. These are made of three subatomic particles, which are protons, neutrons, and electrons. Now, while they're all made up of these particles, the particles can be rearranged to form, well, different combinations. The type and arrangement of these particles, meaning how many protons, or many other things for that matter, determine the properties of this matter. And that is actually one of the main reasons they can form in different states. So these are generally sorted into three states: solids, liquids, and gases. So each of these states have different properties that kind of go with them. The first one we're going to talk about are solids. Every solid will have a definite shape, meaning if you think of a block of wood. I know, I'm an artist, it's awesome. This block of wood will always look like this block of wood. If I drop it on the ground, it will look like a block of wood. The only time this will change if I cut it up or something. But even then, I can probably put the pieces back together and say it still looks like a block of wood. That's the definite shape. This block of wood, I can't really shrink. Can't really make it bigger. I can break it into smaller pieces. But again, I can put them back together and they would still take up the same amount of space. That's the definite volume. These particles are actually held together very tightly. So imagine these are the atoms. They're very, very, very tight and very, very orderly. And this shape is independent of container, meaning that block of wood will look very much like a block of wood on the ground, or in a container. That's supposed to be a container. I'm not good at art, we get that. But it's still a block of wood no matter what it's in. That is a solid. Liquids have indefinite shapes, meaning they don't really have a set defined shape. So if we think of, if I were to ask you what is the shape of water, you really can't quite tell me. So water can sometimes be, the shape like this if it's in a bottle of water. Water can also look like a puddle on the ground. Water can really, look something like this if it's in a special container. So it forms whatever shape is dependent on the container. It also has, however, a definite volume, meaning if I were to take this amount of water and we'll say spread it out, I'm not going to suddenly have more water. For example, if we have two bins, and let's pretend that I take this amount of water and pour it in here, and I end up getting that it looks like that. If you actually have a younger brother in preschool or something, you can ask him which one will have more water. The normally point is this one. It looks taller. It looks like it has more water. But it has a definite volume, meaning these are the exact same amount of liquids. Nothing is changing, it's just in a different container. The particles, though, when you look at them, look less orderly. They're pretty close to each other. but they're loosely enough they can actually kind of slide past each other, which allows water and other liquids to flow. Lastly, though, we have an indefinite shape and indefinite volume. It'd be like trying to imagine what does air look like. We don't know. You just don't. That's because it's a gas. Technically, air is a mixture of gases. We'll get there in a bit. But indefinite shapes. Indefinite volume also means that if you have a container, we'll say this small, and a container this small, the same amount of gas can actually fill up both containers. Now, it'll be a lot more, concentrated in this one versus this, but you can still actually technically fill up the entire container. And the particles actually, when you look at them, are not even touching each other. They're kind of doing their own thing and bouncing around everywhere. That's the gas. In our next section, we'll be talking about classifications of matter. These are our three objectives. Basically, they summarize around you being able to classify matter. In addition to our three main states of matter, which again are solids, liquids, and gases, matter can be classified into four other classifications: elements, compounds, homogeneous mixtures, and heterogeneous mixtures. These can be grouped into two categories: pure substances and mixtures. Now, we're about to actually discuss this even farther, but before going on, I want to point out that our pure substances are going to be our elements and our compounds, and our two mixtures are our homogeneous mixtures and our heterogeneous mixtures. So our first of our pure substances that we're going to talk about are elements. These are substances that cannot be broken down any farther and keep their chemical identity. Individual constituents of these are atoms. So an example of this would be carbon. Okay? If you were to find a sample of carbon, individual carbon would come in atoms. So carbon, 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 carbon. Normally, it will look more like this. Carbon tends to be a solid. But elements are basically things that you cannot break down farther and still remain their original identity. Compounds, however, are made of two or more elements. Individual constituents are molecules and ions. So for example, if I have two hydrogen ions and one oxygen atom, that could be H2O. And when I actually find, or if I have a sample of H2O, the individual samples of it are all going to be molecules. So a whole molecule, not just the atom. That's what we mean by individual constituents. When we actually mix pure substances together, we have two types of mixtures that can form. Our first type that we will talk about is a homogeneous mixture. This is when we have a perfect blending of two or more substances with each other, and it will have a uniform composition throughout. This means, so let's say we've got a sample of, something, and it has stuff mixed in. Now, it's not really an actual good illustration. I'm trying to show it actually evenly distributed. So I guess after you stir that up, it would just look like this. But anywhere in this should look the same. So if I have something at the bottom, and I have samples that look different, that is not a homogeneous mixture. So, sorry, that was actually a bad example. But anything that is the same all the way through, and it's kind of very smooth, if you will. Common examples can be vanilla ice cream, creamy peanut butter, water with food coloring mixed in it. So, yeah. Our second type of mixture is a heterogeneous mixture. This is an imperfect blending of two or more pure substances with each other. This is where there's a non-uniform composition throughout. It's not actually blended well together. So if I had a bowl of ice cream or something, right, that really does not look like ice cream. So we'll say a cone of ice cream, and it's chocolate chip ice cream. If I take that sample and that sample, this one is basically ice cream without chocolate chips. This one has chocolate chips in it. This is therefore a heterogeneous mixture. It's not smooth. So if you can take two different samples from this mixture and they be different, it's heterogeneous. So examples can be cookies and cream ice cream, crunchy peanut butter. Yeah, that's a heterogeneous mixture. In this next section, we're talking about the difference between physical and chemical changes. And these are our three objectives for this section. Every type of matter has certain properties associated with it. These properties can be separated into two categories, physical and chemical. What I mean is, every type of matter has certain things about it that make it different. And these things that make it different, we call properties, are separated into those two categories. A physical property is a property that can be observed with the senses and can be determined without destroying the object. For example, height or weight or color. You can see these things, you can determine these things without damaging the substance. Chemical properties, however, indicate how a substance reacts with something else, and the original substance must be destroyed to observe a chemical property. For example, flammability. You have to try to light something on fire to see if it's flammable. Or, conductivity. You have to actually send an electric current through something to see how well it will conduct electricity. Now, matter commonly undergoes changes. These changes are also physical or chemical. A physical change is when we change the form of matter without changing the identity. So for example, ice, which you could think of as an ice cube, to water, now ice is basically the solid version of water. Water is the liquid, but they're all still just H2O. It just simply looks different. So state changes, anything where it's just something that is already there is now changing appearance, is a physical change. A chemical change is one where the original identity of the substance is changed and an entirely new substance is formed. For example, if we have a piece of wood and we burn it. When you burn this wood, eventually you'll be left with a pile of ash and random smoke will occur. These are completely different. The wood does not equal the smoke. It does not equal the ash. It is a new substance. Now, there are four evidences of a chemical change. A transfer of energy. You can think of something being hot or cold. Change in color. producing a gas, or forming of a precipitate. If just one of these occur, it's probably physical. But if more than one occur, it's likely a chemical change. For example, if I put food coloring in water, I have a change in color, but that's just a physical change. Nothing's really changing. When I cook an egg, however, the egg goes from being, an egg. We then put it in a frying pan, and eventually it'll turn yellow. Now, we have a transfer of energy because it's now hot. The yolk, technically originally, I'll give you that, it was kind of clear actually, has now changed color and is mainly yellow, or some of it's white. It smells better, so it produced a gas, and it's now fluffy because we have a precipitate formed. That is a chemical change. In this next section, we're going to learn about the train track method. Those are your objectives for the train track method. And yeah. Most of chemistry involves the studying of the changes that occur due to reactions. But it is important to know how these are measured and what units we use to do so. Before we begin actually using these measurements, though, we need to learn how to convert between units. We will use a process called dimensional analysis. Dimensional analysis is a unit conversion technique that relies on the fact that multiplying any number by 1 retains the value of that number. For example, 2 times 1 is equal to 2. Just like multiplying a measurement, for example 2 meters, will retain the measurement. A set of measurements that represent an equal measurement but in different units is called a conversion factor. For example, 12 inches and 1 foot represent a conversion factor. Also, 60 seconds and 1 minute. Those are conversion factors. They are commonly expressed as fractions, so it'll actually aid us in converting units. Notice these are the same fractions, just flipped. Since the above conversion factors represent equal measurements, multiplying a measurement in one of these units by the appropriate conversion factor will change the unit it is reported in, but not the magnitude of this measurement. This allows us to convert between units. So in order to convert between two different units, you multiply the measurement by a conversion factor in such a way that the original unit is canceled. This will occur when the original unit is on the bottom of the conversion factor. So, to give you a hint, think of when you multiply fractions. If the same numbers on top and bottom, we can cancel those out and be left with 3. So you'll be seeing a lot of those type of canceling out coming up. To do what we call the train track method, which is our way of doing dimensional analysis, first, you list all conversion factors that you know that may be helpful. If you think of too many, that's okay. It's better to have too many than too few. Secondly, you draw 2 lines in the shape of a plus. This, especially as it grows, will be our train track. Now in the top left corner, write the unit that you are given. Start with just the unit. We'll do the number later. Now, in the bottom right corner, write the unit you just wrote. This makes units cancel out. In the top right corner, write whatever unit you're ultimately trying to get to. Now, we've just been using units, so now step 6 is actually to put numbers in. Every track piece should represent a conversion factor. These numbers should match what you wrote in step 1. Now for every track piece, again, the top measurement should be another way of expressing the bottom measurement. Lastly, we multiply these together. Your train track will eventually look something like this if it gets long enough. So first, we multiply all the top numbers together. Then we multiply all the bottom numbers together. Then finally, we divide those numbers at the end. This saves us some time with dividing. That's often where most errors come in, and it makes the process a lot more simple. Your final answer is this number with your correct unit, which should be coming from the last top section. Well, how many minutes are in 2 hours? Some useful conversion factors we have. I'm just thinking 1 minute equals 60 seconds. I know that 1 hour equals 60 minutes. And, well, I think that'll be enough for me. So we start by drawing a plus. We are given hours. So I put that unit up here. Then I immediately write that down here. This will allow us at the end to cancel out hours. I'm trying to go to minutes, so I can write that up here. If I have something that relates minutes and hours, I can do this. If not, I may have to extend my track a bit. So I look back at my conversion factors and I see I've got something that relates these. So I can start putting in numbers, because that is as far as my track will need to go. I will go from hours to minutes. So I start with 2 hours, and I know that 1 hour, 60 minutes. So, lastly, we multiply. So, 2 times 60 is 120. There's nothing to multiply the 1 by, so we just have a 1. We divide those at the end to get 120. And I'm in minutes because the hours cancel out. There you go. How many feet are in 14 yards? Well, this tells me that 3 feet is equal to 1 yard. That actually relates the two things I need, so I don't need any other conversion factors. On the previous example, we had extra conversion factors. We didn't use them, and it's okay. So if you know conversion factors that get you where you need to go, you don't need any more. So we draw our plus. We're starting with yards. So that goes right down here. We're trying to go to feet, and we do have a conversion factor that will connect it. So we now put in numbers. 14, 3, 1. Let's make sure that these are indeed the same a conversion factor. They represent the same measurement. So 14 times 3 is 42. Again, 1 has nothing to measure, multiply by, so that just goes to a 1, which gets us 42 feet. And that's our final answer. There are 42 feet in 3 yards. Sorry, 14 yards. Lastly, how many inches are in 6.5 feet, which is approximately how tall I am? Now it's important to know that 12 inches equals 1 foot. Well, that's again, be able to relate inches to feet. That's all we need. So we start with feet. That means feet go right down here. We're trying to go to inches, and we do know a conversion factor to relate them. 6.5 feet, 12 inches, 1 foot. This represents one conversion factor. So we have 6.5 times 12 and 1, which is, I believe, 78, divided now by 1, which is 78 inches. That's our final answer. Now, there are many times that, unlike the previous example, we're going to need multiple conversion factors, not just one. In these cases, you simply add track pieces until you fully cancel out the original unit, and you are now in the desired unit. So here's a few extra points that may help. First, always list all conversion factors that you know that may be helpful. Having too many is okay. Second, start the track with the given amount in the top left. Anytime you add a piece of track, immediately write its top unit in the bottom right section. So if I have to write something here, I add a new section and write that down here. The only time you won't need to do this is if you're actually in the end unit that you want to get to. But this automatically helps you keep things canceling out. And number 4, check your units to make sure they cancel out before moving on to a new problem. All right, for this example, we are trying to convert 2 weeks into seconds. So I know that there is 1 week in 7 days. 1 day, 24 hour. 1 hour is equal to 60 minutes. And 1 minute equals 60 seconds. That should be enough to get me there. Draw a pretty long line. We are starting with weeks, which means I immediately put that down here. The only conversion I have, factor that involves week, requires me to convert to days. So I put days down here. The only one remaining relates out to hours. Hours must be related to minutes. And minutes are finally related to seconds. And I'm not going to write anything over here because seconds is where I need to end. So I now put numbers in. 2, 1, 7, 1, 60. Oh, not 60. 24. 160. 160. Which, when I multiply out, gives me 1,209,600. And the bottom multiplies to 1, which equals 1,209,600 seconds in 2 weeks. So, week, days, hours, minutes, seconds. There you go. How many inches are in 2 miles? Well, I know that 1 mile is equal to 5,280 feet. I know 1 foot is equal to 12 inches. I also know, though, that 1 yard is equal to 3 feet. That may not help me, but just in case it does. So, we start with miles. Put miles down here. The only conversion factor I know relates that to feet. Feet. Now, I have 2 conversion factors that use feet, but ultimately I'm trying to go to inches. So, since I can relate them directly to inches, I'm not going to go through yards. So, now I put in my numbers though. 2, 5, 2, 8, 0, 1 mile, 12, and 1. When I multiply all those together, I get 1, 2, 6, 7, 2, 0 on top, and 1 on bottom. When I divide those, I get 1, 2, 6, 7, 2, 0 inches. And that's my answer. In our next section, we'll be talking about SI units and the metric system. That is our main actual objective for this section. Now, the SI units are the standard system of units that are used worldwide. America does not use many of these, but they are still important to know. These are the SI units. On the left represents what they're actually measuring. This column represents the actual unit, and this is our abbreviation. Those are the SI units. In addition, a very common and useful system of measurements that we will use in chemistry is called the metric system. Now, the metric system, in short, is a series of prefixes representing a certain amount of whatever the base unit they are representing. It is based on powers of 10, and this allows us to convert units very easily. For example, 2 units in the metric system that we will use are kiloseconds and milliseconds. The kilo and the milli are both prefixes that are talking about our SI unit for time. Now, these do not have to deal just with SI units, but they commonly will in chemistry. So, these are the main prefixes. There are more. The main you care about are these, but nonetheless, they're useful. So, the prefix for kilo, for example, is K. Commonly, that is known by an exponential multiplier, but this says that in 1 kilo something, there are 1,000. Or in 1 deci something, there's 0.1. So, for example, in 1 decimeter, there's 0.1 meter. So in 1 centimeter, there would be 0.01 meters. So, a little bit confusing. There are different ways to look at this. I will discuss this later in the year, but for now, I'm going to show you how to use this chart. That way you can always come back to it. You can always have something that will always work. And most places will teach you this chart, and then they'll move on and say, here's a different way to do it. So, let's actually try them. Let's try kilometer to centimeter. Now, I don't know anything that relates kilometer to centimeter. But I do know from that previous chart that 1 kilometer equals 1,000 meters, and 1 centimeter is equal to 0.1 of a meter. Now, yes, You can think of this as 1 meter equaling 100 centimeters. If you want to do that, you are free to do so. But that's the last I'm going to mention of it. So, we start a conversion factor, kilometer, which goes right down here. I don't know something that relates kilometer to centimeter, so I have to go to meter, which means meter goes down here, and I can finally put centimeter up top. So 4.2, 1,000, 1 kilometer, and 1 centimeter, 0.1 meter. When I multiply the top, I get 4,200. The bottom, I get 0.01. And that, when I divide those, gets me 420,000. My unit is centimeter. So the same thing as the train track method, you're just using different numbers. So same exact process. Let's try the second one. We have deciliters to megaliters. Well, we know that 1 megaliter is equal to 1 million liters, because that's what the actual prefix for mega means. And I know that 1 deciliter equals 0.1 liter. So we start with deciliter. That goes down here. Up here goes megaliter, because that's the, I'm sorry. Up here goes liter, because I can't relate deciliter to megaliter. Liter goes down here. Megaliter finally goes up here. And we can put our numbers in. 1, 0.1, 1 million, and 1. So that gets us 119.23 over 1 million. When you divide that, you get 0.123341923 megaliter. And that's our final answer. Oh, wait. Yep, we're good. Other useful pieces of information are that 1 centimeter cubed is equal to 1 milliliter, meaning if I were to draw a cube, let's try that again. If I were to draw or make a box, and this box was a centimeter by a centimeter by a centimeter, and I were to fill that box with water, that would be 1 milliliter of water. So, and 1 decimeter cubed is a liter, 1 meter cubed is a kiloliter. So, they'll use this quite often. Those, the bottom two, not as much. Alright. In our next section, we are talking about significant figures and scientific notation. Commonly, I will call significant figures sig figs. So, don't let that confuse you too much. When writing in numbers in chemistry, we often are not as certain as some measurements when compared to others. Sig figs are a method that scientists actually use to ensure their calculations are only reported as accurate as their least accurate measurement. So you may, if you have to take a guess on something, that will limit the accuracy of any measurements based on that guess. To determine the number of sig figs in a number, we have two different options, if there's a decimal and not. If there's a decimal, start the first non-zero from the left and count it and every number after it to the right. If there is no decimal, all non-zeros are significant, trapped zeros are significant, trailing zeros are not significant. Trapped zeros are, for example, 1, 0, 1, and trailing zeros would be 0, 0. So, how many sig figs are in the following numbers? Well, 1035600. This 0 is significant. So is that 1, 3, 5, and 6. But these zeros are trailing, so they don't count, meaning that one has 5. This one has a decimal. Our first non-zeros are 5. So we count it and everything to the right for a total of 3. There is a decimal, and our first non-zero is a 1. So we count that one and everything after it to the right, which gives us a total of 7. This one actually does have a 0, so we count this too and every single 0 after it. They're only trailing zeros if there is no decimal. So in this case, we have 8 sig figs. There is no decimal in this last one. None of those matter. There's 1 sig fig. When performing calculations, we need to keep our measurements down to the sig figs of our least certain measurement. When we're adding or subtracting, do not keep trailing columns that are after the decimal, and always round to the last non-trailing column. When multiplying or dividing, keep the smallest number of sig figs, always. Round if you have to. For these next equations, in our first one, there are 2 sig figs, and in 301 there are 3. When we multiply this number out, we get 6923. But because of 2 sig figs, we need to actually round such that this number only has 2. There's 1, there's 2, that means we need to round these, which turns into 6900. 10.2 times 5 gets us, I believe, 51. We have 3 sig figs here and only 1 here. We have to round to that 50, which gets us 50. 100 plus 14 minus 0.9, I'm going to write that over here. What you want to do is actually line up the decimal. So when you actually add these, you get 114 minus 0.9, which is 113.1. Now, this is a trailing column because there are other numbers that do not have decimals that accurate, meaning we round to this place. This ends up being 113. For 120 minus 12, I'm going to erase these answers. So you get 120 minus 12 plus 1.2 minus 0.12. Which gets us, let's see, 108, 109.2, 109.08. We have a trailing column here and a trailing column here, which means that we round to 109. Finally, if we are working with a very large or very small number, we will often convert that number to scientific notation. In general, if a number has 5 digits or more, your notes may say units. Sig figs. We convert it to scientific notation. It's not quite a set rule, but that works for most cases. To convert a number to scientific notation, move the decimal from where it is currently to a place such that there is only one non-zero to its left. Round this number then according to how many sig figs you need. Thirdly, if you moved your decimal to the left, your exponent is positive. And if you moved your decimal to the right, your exponent will be negative. So finally, we write the rounded number from part 1, and 2, write times 10, and put the amount of spaces that we moved as the exponent for 10. Now keep in mind this positive and negative version. So let's get some practice. All of these are to be with 3 sig figs. So 7, 4, 8, 9, 4, 8, 9, 8, 4. Our decimal is currently here because I don't see it anywhere else, so it's going to be after it. The only place such that we can have a decimal where there's only one non-zero to the left is here. So we need to move our decimal 1, 2, 3, 4, 5, 6, 7, 8 spaces. We moved our decimal to the left, which means this is going to be positive 8. And 3 sig figs will be right here. All these don't matter to us. This will round up to a 9, and we get 7.49 times 10 to the 8th. For our next number, right here is where our decimal should be, because that gives us only one non-zero to the left, which means our decimal has to move to the right 1, which means our exponent will be negative 1. That gets us 1.00. Again, we need 3 sig figs. 1, 2, 3. Times 10 to the negative first. I know that ignores a lot of the numbers, but that's just kind of how scientific notation works. Our last one. Our decimal should go right here. That's 2 spaces, and we move to our left. 1, 2, 3, 1.00 times 10 to the second. If this doesn't make sense, scroll back in the video. Often seeing this a few times is really what people need. For our last section in Unit 1, we are talking about inorganic nomenclature. We are getting part of it this unit. We will talk about some more in our next unit. All compounds have a name that's associated with them. Use of the wrong compound can pose some serious risks in the laboratory or result in the loss of numerous points on, homework or even tests and assessments. So the first compounds that we're going to talk about are called binary ionic compounds. Binary means 2. Ionic means ions, and they are bonded together to form a compound. Typically, this will be a metal and a nonmetal, or a metal and sometimes a group of nonmetals. Later on, we'll explain this, but for now, we're going to call the metal the cation and everything else the anion. First, we need to name the cation. Now, this name is either the metal's name if it's not a transition metal. Remember on the periodic table, transition metals are here. So if it's in there, or if it's not in there, it's just the metal's name. For example, sodium. This is over there somewhere. If it's a transition metal, you need a Roman numeral indicating its charge. For now, you'll be given them. Later on, you'll be told what it is. And if there are no metals, then you need to look on your common ion sheet and figure out what compound is there and what its name is. Secondly, we name the anion, which is basically everything else. If this is just one nonmetal, then the name is going to be the nonmetal's name, but ending in "ide." For example, chlorine is now chloride. If it's more than one nonmetal, then that's probably going to be on your common ion sheet, and you use whatever name is given you. Let's practice. CaCl2. Our metal is calcium. It is not a transition metal, so we use calcium. That is just one nonmetal, so it's going to be chloride. Now I hope you notice I never said anything about caring about that subscript, because for binary ionic compounds, you don't care. It's not calcium dichloride or whatever, just calcium chloride. Sodium is a metal. It is not a transition metal. So sodium chloride. Copper is a transition metal, but they told us our charge is 2+, so that's going to be copper 2, because that's our charge, chloride. Down here we have sodium, but you'll notice it's not just one nonmetal. On your common ion sheet, though, you'll find this is called sulfate. And this compound, therefore, is sodium sulfate. Up here we have iron, which is a transition metal. It is 3+ charge, so iron 3 oxide. Again, all of these follow this naming because we have a metal and some nonmetals. That's called ionic compounds. This is iron 2 oxide, potassium. That NO3 is from your common ion list, and it is nitrate. Now down here, we don't actually have any metals. But you will notice, though, that on your common ion sheet, this is all one ion, and this is another ion. This ends up being called ammonium nitrate. The second type of compound we're going to name is an oxyanion. Now, oxyanions consist of just a nonmetal and an oxygen. And while the naming that we're about to learn will not actually help us know exactly how many oxygen there are in a compound, it will help us know relative to another compound. I'm mainly explaining what the actual suffixes mean. Most oxyanions you need are on your common ion sheet. This set of rules lets you know what the prefixes and suffixes mean. So in order of increasing amount of oxygen, hypo something ite is less than something ite is less than something 8, which is less than some per something 8. So ClO is hypochlorite. Sorry, that's supposed to be one word. Which says that this should have less oxygen than chlorite. Well, ClO2 is actually called chlorite, and you'll notice that hypochlorite does have less than chlorite. Down here we have nitrite, which says should have less than nitrate. Well, this is nitrate, and you'll notice 2 is less than 3. Our next type of compounds are binary molecular compounds. These are when we have 2 nonmetals. Please keep that in mind that you will only use these for 2 nonmetals. They will use the following prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. First off, you name the first element using any prefix except mono. So if there's only one of the first element, you just simply put the element's name, not mono. And the second element uses any prefix, including mono, but you ended with "ide." So, 2 exceptions. H2O is not dihydrogen monoxide. It's called water. And NH3 is not nitrogen trihydride. It's ammonia. So, up here, we have 2 chlorine, 1 oxygen, dichlorine, monoxide. Diphosphorus, tetraoxide. We have only 1 carbon, but we don't put mono. Carbon. We have 1 oxygen, and it is the second, so we can put monoxide. Diphosphorus, pentaoxide, dinitrogen, trioxide. Finally, we have a unique set of elements called the diatomic molecules. These always occur in pairs when they're by themselves. Anytime these elements are used in chemical equations by themselves, their natural states, they should have a subscript of 2. These are the elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, which can spell Hofbrinkel. This says that H plus O to form water actually should be H2 plus O2 to form water. Neither of these equations are balanced. It's okay. We'll deal with that later. That is Unit 1. Congratulations.